yesterday. Those are my son's notes. All my chemistry notes. Actually, that looks too advanced for my child because he's only 2. That must be my wife helping him draw. This will be on the exam, so make sure to take detailed notes on that. Watching him play with the iPad with the stylus is the most terrifying thing. He like mashes the tip into the screen. I'm terrifying, but he's also really sweet and like horrific. If you take things away from him, he's like, I'd rather just see the iPad break, just buy a new one and have to listen to him scream. Not like because I hate listening to him scream. I just, makes me sad because he's my kid. And okay, so anyways, so we left off talking about the method of initial rates. This is, where am I? I'm in like this is correct. Oh, because that's from office hours. Okay. Let me copy and paste this. So yeah, so we were looking at the method of initial rates. This is sort of the beginning for kinetics. And we looked at rate laws. I kind of talked a lot about, I don't know, I try to convey some of the differences between thermo and kinetics. Bring my son to class. I would love to bring him to class. He will like rip the microphone down and like smash it into the side. I don't know. I'll bring him one day. Before I had a child, I used to take my dog to class. Well, before I had a child and before it was a pandemic, I'd take my dog to class sometimes. That was pretty fun. For exams, at least. Okay. All right, yeah, so we're talking about the method of initial rates, and we're kind of talking about experimentally what you end up doing here is you just hold one thing constant. So like in between experiment 1 and 2, the ammonium concentrations are held constant, but you can see that the nitrite concentrations are changing. And this is what you would do naturally. 2-year-olds do have untapped wisdom. They are very joyful, like he's a very happy boy. That's a nice thing about kids. They bring you joy every morning for no reason, it's like their natural state. So being a parent is easy. It's just making sure you don't snuff out that happiness. As an instructor in college, that's my job, is to snuff out happiness. But as a parent, it's the opposite. I'm kidding. Obviously, I love you guys. I know that chemistry is not usually a favorite course. This one's not that bad, but organic chemistry, I can like feel the students just like getting crushed emotionally by it. Okay, so yeah, so what we're trying to do here is we're just trying to figure out we're just trying to take and figure out what X and Y are here. And so the way that we do that is we look at how our rate over here changes as we change one of these concentrations. So I hold ammonium constant and I half the concentration of nitrite. And so what happens to my rate between 2 and 1, we know that because we're controlling all the variables and only changing the concentration of this, it must be dependent on that. So in going from here to here, my rate is halved when I halve the concentration. And if we look at the other one, I'm trying to think how you can set this up mathematically, but if we look at the other one, we see that when we double the concentration of ammonium, we more or less double the concentration of our rate, or we double, not the concentration of rate, but we double our rate. And so when the change in concentration and the change in rate are proportional like that, where like having one halves the rate, then the exponent is just equal to 1. So our rate for this just ends up equaling, oops. Raised to the first power, oops. Raised to the first power. And so these powers that are here we refer to as the order of the reaction. So so this reaction has an order of 2, and we call that second order. And so the language that we use around this would be the reaction here. It's first order in ammonium and first order in nitrite and second order overall. So it's first order in ammonium, meaning that for ammonium, it only depends on the concentration, like raised to the power of 1. And it's also first order in nitrite. So again, that just means that the way to think about it is that, like, in order for the reaction to go at whatever what we'll talk about this more in detail, but at the step in the reaction that determines the rate, it only requires 1 molecule of nitrite and 1 molecule of ammonium to react. So it's first order in this, meaning I only need 1 of these, and first order in this, meaning that I only need 1 of these. But it's second order overall in the sense that at that step, I have 2 different molecules or compounds that have to bounce into each other. Yeah, determining X and Y comes from, so if you want to set it up mathematically, we can take and say, let's look at the first one. So like, if we look at this one, I'm trying to understand how this change between here and here is related to this change here and here. Let me take this. So if you want to set it up in like a really strict, sometimes you could just do it by observation, which is what I did there, but you can also set it up this way. So you can take the first rate and divide it by the second rate. You can usually make yours, like, it doesn't matter whether it's rate 1 or rate 2 or rate 2 or rate 1, but put the bigger number on top. I think makes your life a little easier. I'm going to leave the units off on the rate because they're going to cancel out anyway. So if we look at sort of the ratio there, and going from 2 to 1, my rate changed from 2.7 to 1.35. And we can relate this to the concentration by just taking 0.01. Let me make sure, yeah, rate 2, so 0.01. So I'm taking this one and putting it over the concentration that we had for, sorry, rate 2. So rate 2, I'm putting at the top here, I have the second rate, and then I have the concentration 2 as well. So these numbers are going on top. And on the bottom, I'm putting these numbers. And then in order to figure out what the, let's see, in order to figure out what the order is, I raise that to the power of m. That's what I'm trying to solve for. And then I just go through and I solve this. So 1.35 times 10 to the minus 7th. You can see why I can do this in my head. 1.35 goes into 2.72. So this reduces to 2. And so you end up with 2 is equal to 0.01 divided by 0.005, which is also equal to 2. So now I'm trying to solve this equation. 2 equals 2 to the m. Or actually, I should call this by what I keep my goddamn variables constant. We're looking at nitrite. So yeah, so this is for solving for y. Yeah, so 2 is equal to 2 to the power of y. So this is the equation essentially you're setting up. You're taking and you're dividing one rate by the other, and then you're looking at the concentrations divided, and you're raising those to some power, and then you're solving for that. So when it's simple and like doubling the rate or having the rate has, doubling or having the concentration has the exact same effect on the rate, then it's very easy to solve for y. Y equals just 1 there. And we can do the same thing over here for the other one. So if we take rate 3, so now we're looking at, I don't know, these colors are really helping us very much. It's making me more confused. If we look at rate 3 here, and we look at rate 2, okay, we've changed the concentration of ammonium and going between these two. So now we're looking at the effect of that concentration. So I put rate 3 over rate 2 because it's easier to put the bigger number over the small number. You end up with a whole number at the end instead of some weird decimal. And again, you end up with the same thing. So you'd say, okay, well, this is 2, and then this ends up equaling 2 to the x, and so x equals 1. So that's where those come. So that's first order, yeah. You know, it's not always exactly like this, so it doesn't have to be 1. It's obviously the easiest situation to solve for, but it's some multiple that works out it works out nicely. You can end up in situations where like maybe you end up, because it depends on the question. So sometimes the way they set it up, so here they're giving it to you such that these numbers work out really nicely. This goes into this exactly too. But for sometimes in the textbooks, they like to give you something that emulates what real experimental data looks like, where it's kind of noisy. So it might not be exactly 2, it might be like 2.3 or something. In that case, you just kind of round down to 2. So if you end up with some decimal or something, you kind of do your best to approximate what it is. But so this is what allows you to kind of get the overall rate for the reaction. And the main thing here, or a key takeaway that's kind of outside of this math part, is that I'm trying to look at my reaction here. What did we do? We did ammonium. I'll just say this over and over again throughout this chapter, because I know it takes a little bit to switch, is that in order to figure out what all these different things were, the powers, basically the order of this reaction, just remember it's not related to these coefficients up here. Like here, it coincidentally works out that yes, it's first order and these also have coefficients of 1, but that's not where those numbers are coming from at all. In order to figure out what those numbers are, we have to go through some sort of experiment. And here we did this experiment where it's method of initial rates, and that's how we figured out x and y. So if you're not given any experimental data and just given the overall reaction, then we don't know what the order of the reaction is. We need more information. And there's a bunch of different ways you can figure out the order of the reaction. The method of the initial rates is the sort of like, it's just like the first one that we teach. I don't know how, I've never done kinetics research, is that true? I've never done like super hardcore kinetics research, so I'm not sure exactly like how people work on this stuff. Like in the field, if people use this method of initial rates, I don't think so. But maybe it's like a very easy, I mean, this is a pretty easy experiment to set up, you know. You measure the rate, you change the concentration. So that's how the method of initial rates works, and that's how you can find the order of the reaction from it. So typical questions, I'm trying to think of like ways that you can ask this question. I think generally, almost always the question for the method of initial rates is just asking about the order of the reaction. It's just a way to figure that out experimentally. Okay, so generally speaking, we're not, like if you're imagining like what you're usually concerned with in a chemical reaction, you know, here we're looking at the rate law, which relates the rate of the reaction to these concentrations. So it just tells me, like, if I increase the concentration here, how's that going to change the rate? Usually what you're worried about in a chemical reaction is not the rate as much as you are concerned with like how much time it's going to take for the reaction to finish, or what the concentration is going to be at a particular time in the reaction. And so the rate law, if we take it and integrate it, which we're not going to do because I don't think calculus is a prerequisite for this class. Also, my calculus is kind of atrophied at this point, so I can still do it. I can still do some calculus, but not as good as when I was your age. But we can integrate the rate law. Skip ahead here. And it gives us a different equation that we can use. And we'll see how this is a little bit more useful than the other equation. So the integrated rate law is like a really useful way for modeling how long a reaction is going to take to be over. So if you're like a medical doctor or something, you can think of examples where you're worried about that, right? Like if you're trying to study like if you ever take medication, for example, and you look at the half-life of the medication in your body, that you can kind of determine that stuff using, or you can not just kind of, but you can actually, that stuff is determined using this types of stuff that we're about to learn. It also has applications in like nuclear decay and stuff like that. So this stuff's pretty neat. Okay, so the integrated rate law. So generally when we're looking, so up here when we're doing method of initial rates, the order of the reaction that you come out with, it may be second order, first order, third order. For integrated rate laws, we only look at 3 different scenarios. We look at 0 order reactions, first order, and second order. And part of this is just practical, like, you know, the like a third order or a 2.5 order reaction or something, we'd have to integrate those rate laws. But the other part is just that like this actually covers most reactions. Most reactions are first or second order. It's unusual to have a third order reaction. But we can look at, I'm going to start out just bigger, or just kind of looking at these things in general. So you can write a rate law for what these looks like. So in a 0 order reaction, the rate law is just going to be equal to the rate constant, K, and that's it. So in a 0 order reaction, so remember, when we're looking at the rate law, you know, we're typically looking at something like this. And so if it's 0 order, that means X and Y are both equal to 0. So your rate is not, what that tells you is that the rate is not dependent on the concentration of either the product or the reactant. It's only dependent on whatever this rate constant is. So rate is just equal to K. For a first order reaction, the rate's going to be equal to K times one of the reactants raised to the first power. And then for a second order reaction, the rate is going to be equal to, let's just say it's, some simple reaction A going to B. The rate is just going to be equal to the square of what the reactant is over here. If we integrate those expressions, and do some rearranging, which you're welcome to do. So you're literally just taking the integral. So you'd write out the rate as, let's see, I don't want to get into the calculus, but you could write out the rate as dA dt. So remember, our rate is equal to dA dt. So you'd be integrating with respect to time here, and then doing some rearranging. So if you got some calculus chops, go for it. But then we can take those equations and we can integrate them, and we arrange them such that they're linear. So that's natural log of A is equal to negative KT plus natural log of A sub O. And then for second order, you'd be looking at 1 over A. And we're going to talk about how to use these equations. So these are our integrated rate laws. These are way more useful, generally way more useful than the actual rate law. And the reason is that what this allows me to do, so A sub O is the initial concentration. And you could put like a subscript T on this if you wanted to. A sub T is the concentration at some particular time. Yeah, sorry, that's negative KT. But so this is a nice thing because it allows you, so if you know the rate constant, which is something that you can determine experimentally, that's something else you can get from the method of initial rates. You can also get it from this, but, and you know your initial concentration, which typically you do because you're setting up the reaction, right? So if you're a medical doctor and you're administering a drug, you know how much drug you're giving somebody, or if you're a chemical engineer and you're trying to do like a reaction scale up, you know what the starting concentration is. You're starting with a reactor. So that's like an easy thing to do because this is a known thing. Then I can say, well, like at what point in the reaction is the concentration of the reactant really, really low? Like basically when is the reaction over with, or when does it reach like half of its original concentration? I can calculate that with this equation. So that's what these equations are really useful for. It tells you where in the reaction you are. If you're thinking about it in terms of like, if you want to relate it back to like distance and velocity and those types of things, these equations allow you to relate, like the concentrations are equivalent to like your distance. So if you were traveling at a particular velocity and you wanted to know what time you would arrive at a certain location, you can look at the physics equations. They're kind of like this, right? They relate distance and time. Only here we're dealing with chemistry, so we don't deal with distance, we deal with concentration. The concentration in this sense tells you it's sort of like the distance that you've gone in the reaction to completion. The closer you are to completion, the smaller this number is going to be, and the larger this number is going to be. K is our rate constant. And then obviously time, T is for time. There's a lot of different ways that these equations or these questions can kind of be posed. Generally, or a way, if you work through the homework, you'll see these. If you're given, for example, let's say, let me pull some real data here. Yeah, so let's look at how these things sort of come into play here. So if you've got a reaction, let's look at a problem like this. Oops. Let's say you have this reaction. This is a gas called butadiene. And it's dimerizing, meaning like two of these are coming together. So, you know, C4H6, now I've got CH12. But if I look at this, I can do this experiment where I say, okay, like I go into, so imagine that you're going into the reaction ignorant, but you want to know what order the reaction is. Yeah, I'm about to explain how to determine the order of the reaction. Alyssa, let me come back to that like as I work through the problem. It'll be a little clear what I'm talking about, I think, once I kind of get some data down. So with this stuff, it can be hard, I think, to wrap your head around like what the hell's going on in kinetics, because it sort of conceptually feels like messy. But once you start working through the problems, I think it gets a little bit easier. It's like in the acid-base chemistry chapter. Minus 1 second. Oh, that's the. In the acid-base chemistry chapter, it's like a lot, and there's like it's conceptually difficult, and the conceptual part sort of bites you because like you're having to figure out. There's just a lot to think about in the problems, right? Like how to solve the problem is very dependent on how you interpret the question, if that makes sense. Like you have to interpret the question properly and then figure out what kind of acid-base chemistry thing to do, what approximations to make, etc. In kinetics, even though it's a little bit confusing, there's less of that. It's a little bit more like, you know, you can apply like a methodology that's clear cut for problem solving here. So it's not as bad. So if you're struggling a little bit with the conceptual parts, it doesn't necessarily damn you to not being able to solve problems. And so you can kind of start solving problems. And then I think the conceptual stuff sort of becomes clearer through that problem solving. It's always hard, I think, to explain exactly what the best way is to learn this stuff, just because, you know, people learn things differently. And even though we present things in like kind of a linear fashion of like, this is what you learn, and then you learn this, and then you learn this, it's really like a pretty non-linear process of working at it, kind of understanding parts and pieces, and then having other parts and pieces sort of illuminate themselves as you study. Learning is kind of an inherently, can be, especially when you're having to learn for an exam, like a frustrating process. Okay, so now, so we have this process and we're trying to figure out the order of this reaction. Let's say we're trying to figure out the order and the rate constant. So say, what is the order of this reaction? Let's just start there. And then the second question we'll ask is, what is the rate constant? And so we're asking similar questions that we can ask with the last thing that we learned, which is the method of initial rates. Essentially, what is the order of the reaction? But the data that we're collecting is different. So here we're looking at how the concentration changes as a function of time. So as an experimentalist, what I'm doing is I start this reaction, right? So you can imagine that I'm starting this reaction. So this kind of gets back to your question. I'm starting this reaction, so I put in some amount of butadiene. So I start out with 0.01 molar butadiene, and then I let the reaction go. So I start this reaction, I don't know, maybe you apply heat or something to get it going. And then what I'm doing is that I'm just monitoring how much butadiene I have in the reaction. So after 1,000 seconds, I have this much. So it's going down. And then after 1,800 seconds, it's going down more. 2,800 seconds, it's going down more, et cetera, et cetera, et cetera. So the amount of butadiene that I have is decreasing with respect to time. And so these equations that we looked up here, they're expressions of this relationship. So here I have concentration and I'm looking at time. What do I have here? I have the concentration, well, in the zero order in particular. I have concentration and I'm looking at it as a function of time. This is my initial concentration and I'm looking at how that changes with respect to time. So as the reaction goes, if I'm looking at the reactant, I'm expecting this number to get smaller and smaller. And that's exactly what we see here, is this gets smaller and smaller. If you want to think of a chemical reaction that at least some of you are maybe familiar with, if you've ever taken drugs, illegal or not, you start out, let's say alcohol, since that, you guys are in college. I'm certainly not encouraging or judging or anything. I'm just using it as an example. But, when you drink a whole bunch of alcohol, you're sort of kicking off a chemical reaction at that point, right? You get the alcohol content in your body really high. And so that's where you are here, right? That's your A sub 0, is how much did you drink? And then you start to sober up as your liver processes the alcohol and converts it to acetaldehyde. So at the beginning, it's like I have all this ethanol in my body. And then after a certain amount of time, I have less. And if I could model, I'm sure you can actually do this, you can model how much ethanol you're going to have over a certain period of time using an equation like this. You can say, well, how sober am I going to be after 2 hours? And, you can calculate how much alcohol is going to be left in your body using an equation like this. In a medical setting, same kind of idea. If I'm administering somebody like anesthesia or something, and I want to know how long they need to stay asleep, I could use an equation like this to calculate that. I could say, okay, if I put in, 200 milligrams or whatever of the drug, how long will it take for that to go down to, 10 milligrams to where they're going to wake up? And is that going to be long enough to complete the surgery? So that's what these equations are good for. In a chemical engineering situation, which is probably the least familiar though, you're just trying to figure out when the reaction is done so that you can kind of dump it out. So experimentally, how would you do this if you were trying to kind of figure out what the half-life is for a drug? Yeah, you'd study this in like maybe a group of patients, and you'd measure their blood concentration levels for a particular drug. You might also be able to measure like metabolites in their urine or something like that as well. But yeah, something like that. And then you would do this exact same experiment. You'd say, okay, I gave somebody, like hydrocodone or something, and I'm measuring their blood concentration initially, and then I keep measuring it and measuring and measuring and measuring and measuring and measuring and measuring time. Okay, but if I want to figure out what equation to use for that, I don't know the order of the reaction unless I run an experiment, and that's essentially what you're doing here. But instead of using the method of initial rates, we're plotting the concentration as a function of time. And so the nice thing about the way all of these equations are written up here is they're all written as linear equations. And so what you want to do here is you want to make plots so you make 3 different plots. So let's look at our equations up here. We've got zero order, I'll put them down here so I have room. First order, and second order. And so each of these equations is written in a form of y equals mx plus b, y equals mx plus b. There's also y equals mx plus b. So this is zero order, first and second. So what this tells you is that for a zero order reaction, if I plot a sub t as a function of time, I expect a line. If I plot for a first order reaction, it's first order if the plot of the natural log of the concentration with respect to time is a line. And for second order, we know it's second order if it's linear, if I would plot 1 over a sub t, so 1 over the concentration change with respect to time. And so if I go through and actually do this, I don't know what the zero order one looks like, but if I take, so what I would do now is I would say, okay, you know, this is my original data. I won't be able to plot all of these, but this is my original data. So for the zero order reaction, I would literally just take this and plot it here and look at the shape of it. If it's anything other than a line, then it's not going to be zero order. And then when I want to check to see if it's first order, I would take the natural log of the data I collected. So I would go through and I take natural log of 0.0100, natural log of 0.00625, etc. And I would plot that. And what I would see in this case, I have a plot of this already made. What I would see is that it's not a line. Let me exaggerate that some. And you can go ahead and plot this in like Excel or something if you want. You know, if when I try to fit this, I'm not going to get a line. It's going to go and it's going to be curved. So that's how I know it's not first order. So if it was first order, what I would expect to see is a line there. Finally, what I would go through and say, okay, well, it's not, I'm just telling you it's not zero order. Let's just say it's between first and second order because the logic is the same. Then I would go through and I'd say, well, what about 1 over c sub 4h6? And I would go ahead and do that. So I'd go 1 over 0.0100, 1 over 0.00625, et cetera, et cetera, et cetera. And what I would end up seeing for that is a straight line. So as I plot these points, what I'll see is that they fit a line really nicely. And that's how I know it's second order. So figuring out if it's first order, to get back to that question, because this is sort of the beginning point for this stuff, figuring out when you have this data, where you're looking at concentration versus time, the way to figure out the order of the reaction is to plot the data the way that these equations tell you to. So if I want to know if it's zero order, what I do is I make a graph and say, okay, if I take the concentration and look at how it changes with respect to time, is it linear? If it's a line, then it's for zero order. If it's not, then it's not zero order and I need to try something else. So then I come over and I say, well, what about maybe it's first order? So then I take, again, I look at this equation. If I plot natural log of the concentration as a function of time, is it a line? If it's not a line like what we saw down here, then it's not first order. And I say, okay, well that model, so I have models for these different things, doesn't fit the data. So then I say, okay, well what about if I take 1 over a sub t, so 1 over the concentration, and plot that as a function of time? Does that model fit? And so if that carves out a line, then I know it's second order. So here, when you're trying to figure out whether or not it's first, second order, first, second, or zero order, what you're doing is you're plotting the data and you're just seeing if your models that you've developed work or not. Does this fit that data? This is a line. Is this data a line? No. This describes a line as well. Is this data a line? Yes. So now it's second order. That's how we know it's second order. The other thing to recognize is that because we've written these equations in this form of y equals mx plus b, the slope of the line tells you the rate constant. So note that m here corresponds to k. So x in this situation is t. That's what we plotted here. That's this axis here. The slope of the line, though, is k. This, obviously, k, a linear equation, is not going to describe this properly. But if we look at what the actual fit is here, the slope here, the change in 1 over a with respect to time, the rise over the run, the algebra type stuff, m is just equal to k. So if you want to figure out what the rate constant is, you can just calculate the slope of that line. So you would take, remember that you would take, like in algebra, you could do like y2 minus y1 over x2 minus x1 to get it. You could do the exact same thing here. I'm trying to think if there's an easier way. Actually, you can just plug, an easier way still, instead of actually using the real data, is you can just solve this equation. Since you have this equation and we have all this data, we can actually just solve it. I'll take you through that on Monday. But generally, so your workflow for these types of problems is, one, it depends on how the problem's set up, but you're generally going to plot you're going to plot the concentration, the natural log of the concentration, and 1 over concentration as a function of time. Which is just a fancy way of saying I'm going to put concentration or natural log of concentration or whatever on the y-axis and time on the x-axis. That's a way to say that as a function of time. It means that, one of the variable that the variable that you're a function of, saying that poorly, the y-axis ends up being this, and the thing that it's a function of ends up being on the x-axis. And you see which plot is linear. This allows you to determine, this tells you if it's first, second, or more unusually, zero order. The second thing is, once you know this, and this is what we'll talk about on Monday, you can use the integrated rate law to calculate K. And then you have the other questions you can answer, like, those are more specific, but you can use the integrated rate law to say other things. And we'll look at some of those problems as well. But your first step in any of these types of things, if you're not told, is figuring out the order of the reaction. So everything for all these calculations involves knowing the order of the reaction. And so now we have two different ways to figure out the order of the reaction. One is we can use the method of initial rates, and the other is we can use the integrated rate law, which experimentally is an easier setup, and look at plots of concentration versus time and see which ones are linear. And so now that we kind of understand how to figure out the order, we can look at what we can do with those equations once we have them. So it should give you, this should, if you take 1 over A, Amanda, if you take 1 over the concentration, and plot it, so you don't apply that to the to time stays the same. You're just doing this transform on 1 over the concentration. It should give you a line. Try doing it in Excel so that the data is easier to work with. Well, I don't know, maybe I haven't used a graphing calculator in years, but the plot is not a straight line if it's not the right equation to describe the order of the reaction. So as the experimentalist, you're going in kind of blind. You're just doing this experiment where you're bluntly measuring the concentration as it changes with time. So to use like sort of the drug analogy, you're testing some patient's blood for a drug in it. You're saying, okay, well, at like 0 seconds, they have the maximum amount of drug in their blood. And then at 1,000 seconds, it's decreased some, at 1,800 seconds, it's decreased some more. And so that's like an experimental determination of how the concentration of the drug changes with respect to time. But we don't know what equation describes that. And that's what you're trying to get. You want an equation that describes that so you don't have to do this experiment with every single patient. And so we're trying to figure out what that is. And so we go through and we make these plots where we plot the concentration versus time, the natural log of concentration versus time, and 1 over the concentration versus time. And we take all 3 of those plots. It can only be one of them. It can only be 0 order, 1st order, or 2nd order. So only one of these can be linear. Whatever one is a straight line, that tells you what the proper model is for whatever reaction you're looking at. So, if I see a straight line when I plot natural log of the concentration versus time, that means that this reaction that I'm looking at is 1st order. And I would expect that 2nd order and 0 order would not be straight lines. So a good problem to work through. So the homework has a bunch of these problems in it. But a good way to kind of work through this is to just take this data and make a chart. So take time, 0, 1,000. I'm not going to write it all out because it'll take me forever. 1,800, 2,800, etc., all the way down. Take A sub t, so what we've already given you, natural log of A sub t, and then 1 over A sub t. And you'll have values for these. So I calculate all those values, so I'm making a table. And then I just want to take and make graphs. So I take A sub t and plot as a function of time, and the points will come up wherever. I don't know how they look, but they'll come up there. And then I take this second set of data and do natural log of A sub t over time. And then the last set and do 1 over A So T over time. So you can do this in an Excel spreadsheet or something. And then I look at what I get there. And what I should see is that I only get a line. I only get a line for this one. These are going to be something else, not lines. What the shape is, there's probably a way to kind of think about that and predict it, but we don't really care. They're not lines, so it's not the proper model. That's the idea. That's the whole point of kind of doing this. So once I figure out which one is a straight line, I know what model I can use for that reaction. So, if I'm given data again, if I know that this order, so the power of this is that if I know, let's say once I know this reaction is second order, right? I don't ever have to do this experiment. I don't ever have to do this experiment again. Instead of having to actually go in and measure the concentration at, like, let's say 2800 seconds, I can use this equation to calculate what the concentration will be at 2800 seconds, because I know what the initial concentration is, and I know the time, so I can just calculate the concentration from the equation. So having another reactant, it depends. Yeah, but if you have another reactant and the other reactant is anything other than zero order, then it'll affect it for sure. So if you have like A plus B or something like that, yeah, it'll affect it. I'm trying to think if we see any problems like that, but yeah. Yeah, so what we're looking at here, just a step back, what we're trying to do. Okay, good, Amanda. I had me worried I put down the wrong data or something. But all you're trying to do here is you're trying to figure out what the right model is for your data. Like, these equations are powerful for reasons that are maybe not obvious because we haven't worked through them yet, but they're very useful. But if you want to use these equations to describe your chemical reaction, you have to know what the correct one is to use. And so that's what this first experiment that we're doing is about. That's why we go ahead and graph it. It tells us very quickly what the proper model is for the reaction. Yeah, okay. All right, well, that cleans up Friday. So the rate law stuff moves a little bit fast. Part of that is just being compressed in with the Thanksgiving holidays. But it's not that bad. This material is not that bad. Don't slack off, because I know a lot of you guys did poorly on the last exam. That's not you personally. I mean, obviously you personally did do poorly on the exam, but like, that's nothing to do with you. That exam always sucks. People always do poorly on it. And I honestly don't know what we should do as a department to kind of address that, a curriculum change or spend more time on it. But this material is a little bit easier. And so instead of being like, it's easier, I'll wait longer, just like really kill this chapter or unit so that you do really well in the next exam. And then, that'll help bump up your grade, and you can hopefully drop an exam and everything will be good. Yeah. Curves and that kind of stuff we'll talk about towards the end of the semester. I have to get together with Samoilenko. I know we're in a pandemic right now, so I'm like very sympathetic to that. But I need to make sure we're on the same page with the other instructors and whatever the department wants us to do. So, but anyway, this rate law stuff is great. I'm not sure I'm necessarily conveying how great it is. It's hard in the Gen Chem course somehow to do that, but like, this stuff is really cool. So try to spend some time on it. And I'll see you guys next week. Thank you guys. You guys are so nice.